Good morning, everyone. Welcome to the third day of the Amazonian Symposium on Physics. With no further delay, we are going with the first talk today by Carolina Loureiro Benoni, and she's going to present about bosonic fields and compact objects. Carolina, it's a pleasure to hear you.
Thank you, Haroldo. Good morning, everybody. So, as Haroldo said, I will talk a little bit about bosonic fields and compact objects. So, in 2016, we heard for the first time the sounds of the universe. So, we had the first detection of gravitational waves, which was we already expected to find these a long time ago, but we only were able to detect these solutions, these effect in 2016. And now we are on the fourth round of observations of gravitational waves. During the first three rounds of the observations, we detected 90 signals of gravitational waves, and now we are in the middle of the fourth run, and we already detected more than 100 signals only in this fourth run, which will last until November of this year. So now the detections barely fit in this graphic. And we also have seen in 2019, for the first time, the image of the shadow of the black hole. So we saw first the picture of the black hole at the center of the M87 galaxy. And in 2022, we saw the black hole in the center of our own galaxy. And so with this detection, so with the pictures of black holes and with the detection of gravitational waves, we are now at a point where we can test the limits of general relativity. We can test gravity in the strong field regime, and we are closer than ever to the black holes. But we have other compact objects that can mimic a lot of the characteristics that we see in black holes. So we have a lot of different examples of these compact objects. So Gonzalo told us about one of these examples in his talk yesterday, but we have a lot of different types of compact objects. And this can be so compact that they can have a photosphere, and they can have they can form a very similar image to that we saw of the black hole. So we have to study these kinds of objects, and it's interesting to try to differentiate between them. So to try to find forms that we can say if this is a black hole that we are seeing or if it's something else. We know that only a small part of the content of energy and density of the universe is in the form of ordinary matter, but the majority is in the form of dark energy and dark matter. And dark matter in particular, we can detect only by its gravitational effect in its surroundings. But these bosonic fields, this dark matter will interact with these compact objects and can itself form compact objects. So we have to study how these types of matter interact with black holes and other types of compact objects, and see if this interaction can lead us to something that we can test, we can observe somehow. So I will talk about a few different things. So first I will talk about, so these bosonic fields, they can interact with black holes and can form clouds. So they can get trapped around these black holes and form these cloud solutions. And if we consider the backscattering of these clouds on the geometry, then we can have hairy black holes. We can also have bosonic stars, so these bosonic fields can themselves form compact objects. And we can also have the scattering and absorption of these bosonic fields by compact objects. So I'll talk a little bit about each of these possibilities. So starting with clouds and hairy black holes. So Carlos is going to talk about this in his talk on Friday. So hopefully I don't step too much on his presentation and don't give too much spoilers, but let's see. So yesterday we heard a little bit about these no hair theorems in on the short course. So if we have two two stars, if we have two stars with the same mass and angular momentum, these stars can be completely different because of how these quantities may be distributed along the stars. So just because they have the same mass and same angular momentum doesn't mean that they are the same star. They can be completely different. But for black holes, if we have two black holes with the same mass and angular momentum, then these black holes are the same. So we cannot differentiate them in any form. So this we know through these uniqueness theorems by Israel and Carter. And this led to a conjecture that if we have a collapse of matter in the presence of any type of matter, then the end point, if we form a black hole, then the end point will be a black hole that has only mass, charge, and angular momentum. So it will be a black hole of the Kerr-Neumann family. So this is a conjecture, but it was we have also a lot of no-hair theorems that were proven considering certain assumptions. And in this work by Bexton, in particular, he considers that the a collapse in the presence of a field, a scalar field, but he assumes that this field inherits the the symmetries of the space-time. So we will see that if we relax this assumption, then we can have the formation of bound states around the black holes, and we can also have the formation of hair around the black hole. So in this case, the hair will be a metaphor for anything other than the mass, charge, and angular momentum that we need to completely characterize our black hole. So how can we form how can we have bound states around black hole? So in order to see this, we consider first the effect of the superradiance. So in general, if you consider, for instance, a scalar wave impinging on a Schwarzschild black hole, so a black hole that has only mass, then what we have in general is that we have an incoming wave. Part of the wave is absorbed by the black hole, part scattered back to infinity. And the part that's scattered to infinity has less energy than the incident part. Okay, so this is the case that we are used to. But if we consider an incident wave falling into a Kerr black hole, then in this case we can have some modes. If the mode has a small enough frequency, then the reflected part of the wave can have more energy than the incident part of the wave. That is, in this case, we can have this wave is being amplified by the black hole. So the wave leaves with more energy than it had before, and the black hole mass and angular momentum will get smaller. So it's like the wave is stealing energy from the black hole. So this is what we call superradiance when the wave is amplified by the black hole. If we confine the system, for instance, if we put a perfectly reflecting mirror around the system, then this amplified wave will reflect back in this mirror. So it will bump here, go back to the black hole, and be amplified again. So this will lead to an instability called black hole bond. But if we choose, so this mirror, it prevents this wave from escaping to infinity. So it confines the system. But if we choose a particular value for the frequency, what we call the critical frequency, then we are at the threshold of this instability, and the waves not being neither amplified nor absorbed by the black hole. So in this case, for this value of the frequency, for this choice for the frequency, we don't have anything coming in on or out of the black hole, and this mirror prevents anything from escaping to infinity. So in this case, we can generate a bound state solution around this black hole. So if we consider a fixed background and consider only this bound state, then we have what we call clouds. If we consider the backscattering of this cloud in the geometry, then we can have a hairy black hole. So I'll start considering the cloud solutions. So these cloud solutions were first considered by Hod for the extreme Altair black hole, and he obtained an analytical solution, and then extended this result for a near extremal case, and then we obtain this for the general case. So basically, what we do, we will solve the Klein-Gordon equation for a massive scalar field. In this case, the mass will act as the mirror, so it will prevent the wave from escaping to infinity. And we basically what we have to do is solve this radial equation considering these boundary conditions. So at the horizon, we have a wave-like solution, but if we choose the frequency equal to a critical value, then we don't have neither a wave falling in or coming out of the black hole at the horizon. And here, maybe it's too small, but here we have the mass that basically prevents the mode from escaping to infinity. And when we solve the solution, so here on the left, we have the solution for the scalar case, and we also obtained the solution for the Proca field. So the behavior of the solutions is more or less the same for both fields. What we find is that we find these clouds, they exist along these curves. So this blue curve and this red curve. So this we call existence lines. So we can only have clouds for points that are over these curves or one of these others. So what we see is that when we impose when we fix the frequency, we impose a synchronization condition between the black hole and the cloud. So when we increase the value of this n equal L, so basically when we increase the angular momentum of the cloud, we have the clouds will occur for smaller values of the angular momentum of the black hole. So we have this synchronization condition. When we fix the value of n, but increase either n or L, what we see is that these existence lines move more to the right. So they will happen for larger values of the angular momentum of the black hole. And this happens basically because now we are considering more energetic solutions. So we have to increase the angular momentum to keep these clouds from dispersing. And this behavior with these quantum numbers is similar for the Proca keys. Here, for the Proca case, these full lines correspond to the numerical results that you obtained, and these traced lines correspond to an analytical approximation that is valid for small values of this mass coupling. So the results that I showed you before were for the clouds, and now we can look also for the hairy black hole solutions. So here, the hairy black holes, they will occur here in these shaded blue areas. So they can only occur in these areas. So This for the scalar case and this for the Proctor case. And these domains of the existence, they are bounded on one side by the bald limit that corresponds to the cloud, the cloud's existence lines, so here and here. And this red curve corresponds to the solitonic solutions, so corresponds to uh, uh, bosonic stars. And we see that for the Proctor case, this domain existence, it explains a uh, larger a larger range for the angular momentum of the black hole. So maybe I can talk about this later, but this is these plots correspond to plots of the constant energy density. So this is for the hairy for the black hole with scalar hair, and this is the corresponding solitonic solution. And this is for the hairy black hole with Proctor hair, and this is the solitonic solution with minimum energy for each case. So we see that the hairy black hole is like you can see this as if you put a black hole inside these solitonic solutions, and it kind of deforms its geometry. And a curious thing for the scalar case is that the minimum energy, the solution with minimum energy, it doesn't have a spherical topology. It has a toroidal topology. Okay, now I can talk a little bit about bosonic stars. So as I said at the beginning of my presentation, we have a lot of different candidates for compact objects, for mimickers of black hole. But many of these models, these models, they don't have a clear formation mechanism. So okay, you can imagine that you can have an object that it can be almost as compact as a black hole. So we can mimic a lot of its characteristics, its phenomenology, but how can you form such an object? So for the bosonic stars, this is not the case. So we have a clear formation mechanisms for the solution. And this was studied by Seido and Suen in this work, and it's called gravitational cooling. So basically what happens is that you have the collapse of the scalar field, and as this field is collapsing, at some point it will expel part of the scalar field, and with it will also disperse part of its kinetic energy, and then it will collapse to a dense core. So you have a formation mechanism, and this process occurs independently of your initial conditions, quite independently from your initial conditions. These bosonic stars can be a model for dark matter. But in order for us to see if these bosonic stars are really a viable alternative to black holes, we also have to study if they are stable to small enough perturbations. So this was done already in a lot of works, but we still have a lot to do in this area. So in our work, we considered this action. So we have here an action, Lagrangian related to the field, and we considered both scalar fields, so different models for scalar fields with different potentials. So this for the mini boson star, solitonic boson star, and axionic boson star, and we also consider for the Proctor star. And so basically we have just one second. So we have these equations that we have to solve. So we have here the energy momentum tensor for the scalar case and for the Procca case. And here we have the equations for the fields. And so first we obtain the solutions, the line elements for the stars. So for the unperturbed stars, and then we perturb the solutions and see and study the stability of the solutions. So we consider this to simplify our analysis. We consider only the spherically symmetric case. So this is for the perturbed solutions. So we are considering only radial perturbations. Okay. And so in the end, we find a set of equations that we have to solve. And but these equations, they will depend on this omega square, where this omega is the perturbation frequency. So if this omega, we find that if this omega square is positive, then we will have a stable solution. If this omega square is smaller than is negative, then we have an unstable solution. And when omega square is equal to 0, then we have a transition. So we have a change in the stability of our solutions. Okay, so we have an infinite number of these eigenvalues for these frequencies, but so the smaller value corresponds to this omega 0, and then the other values, they obey these, so they are always larger than this omega 0. Okay, so in order to solve the equations, we consider for boundary conditions mainly that basically we consider that the solution at infinity it goes to 0, so so that we have a localized system. So we consider that the space-time at infinity is Minkowski, and we also consider that the solution is well behaved at the center of the star. So in order to analyze this stability of the solutions, we can look at a graphic like this of the mass over as a function of the central value of the field at the center of the star. And we can use this critical point method. So if we have a change in the stability of our solution, then this will lead to a critical point in a graphic like this. So this point in particular, we know that it corresponds to a change in the stability of our star. So it's stable on one side, and then it's unstable on the other side. But sometimes in the literature, people think that if we have a critical point here, then it will imply that we have necessarily a change in the stability, and this is not true. So this point, for instance, it does not correspond to a change in the stability. So a change in the stability implies a critical point here, but a critical point here does not imply that we have a change in the stability. This sometimes it's mixed in the literature. Okay. So we obtained these graphics of the mass in terms of the central value of the field at the center of the star for each of the models that we were considering. And we see here that for the mini boson star in the Procca case, we have a very similar behavior for this graphic. But here for the solitonic and for the axionic case, where we have a self-interaction of the field, then in these cases, depending on the parameters that we choose, we can have a very different situation. So we can have a lot of critical points on this value, on these graphics, and we can study each of these points to see if they correspond or not to a change in the stability of the system. So here we have a plot of the mass over the radius of these stars. And we see that for the Proca field, we can have larger possible values for this mass of our star, but it's very similar also to the mini boson star case. While for the cases with self interaction, it's very different from the mini boson star case. And we can also see that in this case, when we have the self-interaction, the solution can be more compact than for this case without self-interaction, than for the mini boson star case. Okay, so here we are looking now for the value of this omega square. So when omega square goes to 0, then this means that we have a change in the stability of our solution. So we see here this point corresponds to the maximum of that graphic that I showed before for the mini boson star. So it really does correspond to a change in the stability, but we see that the other point that corresponds to a minimum there, it does not correspond to a change in the stability of our star. This neither for the mini boson star nor for the Proca case. For the solitonic case, we see that we have a lot of changes in the stability. So we have here we have 4 different branches with these changes in stability. And here again, for the axionic case, we also have 4 branches, but we see that this last point that corresponded to a critical point in the graphic that I showed before, it does not correspond to a change in the stability of the axionic star. Okay, and now I'll tell you a bit about absorption and scattering by compact objects. So in order to tell you about this, I will consider a spherically symmetric spacetime that was proposed by Simpson and VII. And this spacetime is interesting to study because depending on the value of this parameter A, we can have a Schwarzschild black hole, a regular black hole, a one-way traversable wormhole, or a two-way traversable wormhole. Okay, so in this way, by changing this parameter, we can compare different situations and see how this changes the absorption and scattering cross sections. So we consider a massless scalar field in this space-time. So for boundary, basically what we have to do is solve this radial equation, considering these boundary conditions. So at infinity, we have an incident wave and a reflected wave. And at the horizon, we have a transmitted wave. And we will look for we will obtain this absorption cross-section. So this is the total absorption cross-section, which can be written in terms of sum of this partial absorption cross-section. So we will do this numerically, but we can also study some analytical, semi-analytical cases. So for the large frequency limits, the absorption cross-section, it will approach the behavior of a particle. So we can study the geodesic solutions in order to see how the absorption cross-section behaves in this limit. And in this case, it is given in terms of this critical impact parameter. So the impact parameter is this distance here. So if I throw a particle here with an impact parameter larger than the critical one, then it will be scattered by the black hole. If it's smaller than the critical impact parameter, it will be absorbed. And if it's equal to the critical impact parameter, it will follow a circular orbit around the black hole. Okay, so this is the solution for the absorption cross-section for the capture cross-section, so for geodesics, but we can also capture some of this oscillating pattern that we see in the total absorption cross-section by considering this sink approximation. So basically you consider that you can have interference between different waves and different waves that are close to this close to the trapped orbit, and then you can find this oscillating behavior that will appear in the absorption cross-section. So this is for the high frequency limit, and for the low frequency limit, well-known result is that the absorption cross-section goes to the area of the black hole. So here we have the total absorption cross-section for the black hole case, so for Schwarzschild and for different values of this parameter A. This dotted horizontal line corresponds to the capture absorption cross-section, so the cross-section for the high frequency limits. And we see that the total absorption cross-section oscillates around this capture cross-section. And we see that this oscillating behavior we can understand better by looking to the partial absorption cross-section. So for each partial absorption cross-section, you have a peak that will correspond to a peak here in the total absorption cross-section. And in here, we have in this graphic, we have the sink approximation. So it's this approximation that I showed here. And so this approximation is valid for large frequency, but we can see that it's very close to the behavior of the numerical solution up to more or less 0.2 of the frequency. Okay, so this is these results that I showed were for the black hole case, but we also studied the case for the wormhole case. So when we look at the total absorption cross-section, in this case, we see that we have some sharp peaks that appear here in the total absorption cross-section. And we can understand better where these peaks come from by looking at the effective potential for this case. So in this in the wormhole case, depending on the value of this parameter A, we can have a potential well here, so that we will have some modes that will be trapped in this potential well. And we see that if we study the frequency of these modes, we see that this frequency corresponds to the frequency of these peaks. And indeed, as we increase the value of A, so we see here in this graph that as we increase the value of A, this potential well becomes more shallow, and at some point it disappears. And if we look at the total absorption cross-section, we see that as we increase the value of A, these sharp peaks get smaller until they disappear completely. We also studied the scattering of scalar field for these types of spacetimes. So we computed the differential scattering cross-section for this case. And we can also look for the for semi-classical, semi-analytical solutions for the scattering case, and which is also given in terms of this critical impact parameter. And if we consider uh, i- if we consider this wave behavior for the particles, and so if we consider that these two particles with impinging with different impact parameters can they can have interference, then we can also anticipate this oscillating behavior that we see in the scattering cross-section by considering characteristics of the geodesics. So here we have these results for the scattering. So here in red, this red curve corresponds to the classical solution, so the differential scattering cross-section obtained using geodesics. This green curve corresponds to the Glory approximation, so it's this one that I was telling you about. When uh, you consider basically you are considering that you have two geodesics, but but these geodesics can interfere. So you kind of endow with the wave a particle with wave behavior. So you can find an approximation for this large angle scattering. And here in black, this black curve corresponds to the numerical solution. So we see that this numerical solution also oscillates around the classical solution, and it approaches this Glory approximation for the large scattering angles. Okay, so this is the solution for the black hole case. And this is the solution. These are results for the, oh, so on this side, we also have results for the black hole case. And then on this side, we have solutions for the wormhole case. So for the black hole case, we see that these scattering cross-sections are very similar to one another, but as we go to larger values of the parameter A, so for the wormhole case, they can be quite different from one another. And one last thing that we consider in this work is because we saw for the absorption cross-section that for frequencies equal to those resonance frequencies, so for the frequencies equal to those trapped modes in the potential, we had those sharp peaks in the absorption cross-section. And so we wanted to see what happened in the scattering case. So what happened with the differential scattering cross-section. So we consider this differential scattering cross-section for a resonance frequency, a resonant frequency, and frequency slightly larger and one slightly smaller to see how the differential cross-section behaved. And what we see is that for the resonant frequency, the differential scattering cross-section is smaller than for these other for frequencies close to it. What makes sense since for the absorption you have a sharp peak, so you have an increase in the absorption cross-section. Then in the scattering cross-section you have smaller values for this case. Okay, maybe I was too fast. So these are my final remarks. So I wanted to kind of give a general idea of some of the things that I've been working with. And so we saw that we can have these bound states around black holes, but I said that they occur only when we have a frequency equal to a critical value. That is true, but these clouds, they can form dynamically. So for instance, if we have a mode with a frequency that is in the superradiant regime, so smaller than the critical value, Then this mode will be amplified by the black hole. The 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 mass and the angular momentum of the black hole will get smaller, and this process will continue until you have and until you reach the synchronization condition, and then you have a critical frequency and you can form a cloud. For the other case, the same. So if you have a mode with a frequency slightly larger than the critical frequency, then this mode will be will get smaller, so it will be partly absorbed by the black hole, and the angular momentum and the mass of the black hole will increase until this condition is obeyed, and you can also form a cloud in this case. So you can form these clouds dynamically. So it's like the system is synchronizing itself. So if you can form these clouds dynamically, you can make these clouds get heavier, and you can also form hairy black holes dynamically. So when I showed you the solutions for the hairy black holes, I mentioned that the solution with less energy, the less energetic solution for the scalar case, it has this toroidal topology, and for the Proca case, we have this spherical spheroidal topology. So there are works that relate this topology with an instability that will appear in these scenarios. So for the scalar case, what they see is that if you start with something with a if we start with a scalar star in this situation, and you kind of evolve the system, then it will be an instability will appear, and it will evolve to a black hole. It will evolve to a black hole. But this instability does not appear for the Proca case, and they try to relate this to these topologies. This difference in the topologies that we have for these cases. So we can say that Proca stars are dynamically more favorable than scalar stars, and this is related to this to the form of these solutions. Can we saw that compact objects can we started saying that these compact objects that they can mimic a lot of the characteristics of black holes, but we can also have very different features from the black holes depending on the parameters of our solutions, and maybe we can use this to differentiate between black holes and compact objects. But we'll need to continue to look for astrophysical observables and try to differentiate between these kinds of solutions. Just a bit of propaganda. So this is the group of gravitation of Salinopolis, which is called Gravitas. So if you want to know a bit more, you can go to our website. It's not very, we haven't updated in a while, but you can you can look there. And this is the team. So here we have the professors that are currently in the group, and here we have the students. So thank you for your attention.
Thank you, Carol, for the presentation and for keeping the time sharp. We have time for some questions. We have questions here.
Thank you. Very, very nice talk. So I was looking at the Lagrangian that you showed at the beginning, the one with the boson fields and the Broca fields. So I was wondering whether, because I've seen that there is some potential term there. So is there a specific kind of potential that you have to set, or I've seen. Okay, I didn't notice this. I see. Okay. Okay, and then I had another question about your last comment concerning this instability in the toroidal configuration. So this toroidal configuration reminds me a lot about what we see in fluid dynamics about black holes, where you can have um, equilibrium configuration in this case, like with toroidal configurations. These are equilibrium. But then if you perturb them and you introduce some kind of instability, you will trigger the accretion process. So in that case, the instability that you have to trigger is a magnetic kind of instability. So I was wondering what is the instability here, and the final state you said it will reach a black hole state. Is this because of the accretion of this boson cloud?
Yeah, I don't remember because it was a while ago that I read this paper. I think Carlos can answer better this, but yeah, basically what they consider is this: you have the solution, and you kind of make you make a perturbation, and you see that it will. I think it's a non-radial stability will appear, and it will cause the system to collapse to a black hole. But I don't remember the details.
Question?
So thank you, Carol, for your very nice talk. So my question is basically a curiosity. So for the bosonic stars, you have considered a massive scalar field, right? I was wondering if you have any sights of what could potentially happen if we consider complex fields, if you add charge to the scalar field. So if I don't know, charge a bosonic star, something like that, could possibly happen.
I don't know. I don't know what would change. Let me see. Yeah, maybe you could have a more compact solution for this case. Yeah, I think maybe you will change the complexity of your solution, because then you have another component that can lead to a more compact solution. I think this, but I mean, for the yeah, this the thing that I can think right now. I don't know how more it could change. I think I maybe can change a lot, but I think like the types of solutions that you can have, I think it will be they would be more or less the same, but you can maybe have more compact solutions in this case.
Right, right. Because I mean, in this case, so if you study only massive charge scalar fields like the absorption and scattering problems, you have this Coulombian repulsion associated to the charge of the field. That's why I was thinking how this could affect the result. So thank you for your answer.
So just a comment, these fields they are complex, right? In the case of the, is this your question if the fields are complex or
No, fair charge.
charge?
Yeah,
You mean scalar charge or
electric charge.
electric
Electric
charge?
charge.
Oh, okay, okay. So these solutions they have in the literature, and I think that there is some kind of repulsive effect. So the stars they get
Ah,
less denser. It's the paper of Jetzer.
what I was going to comment is that for the clouds, because for the cloud case, when you consider the scalar fields, you don't have solution for m equals 0. See, I don't remember. But the thing is that in the Proca case, you have a kind of a locking between the angular momentum of the black hole, the central object, and the spin of this of the cloud. So I don't know if this, if you add charge, this would also contribute in this sense. But
Yeah, it contributes. It's kind of a repulsive
yeah,
between the
yeah.
constituents of the star. And I think it's the paper of Jetzer, one of the reference that you put on the boson star case. And there is a critical charge where you have no stars anymore because the repulsion is so large that the star
Yeah.
do not form. So it's something like that.
Yeah,
There
but
is this study in the literature.
yeah, because we also study the clouds for the case of the Kerr-Neumann case for charged field, and you can have existence lines for both left and right depending on the values of the chart that you choose. Because you can either the have the Coulomb propulsion or attraction, so this contributes in this sense.
So we have time for one final quick question.
So thank you very much for the seminar. And in the same reasoning about the nature of the field, if the field was a fermionic, would we have clouds, perhaps in analogy with the atom or something?
No, for the fermionic case, we don't have clouds. And I saw an explanation on why this doesn't happen. And the explanation was something like this. It's so for the superinion stability, it's like you are putting a lot of particles in the same state. And so for the fermionic case, you cannot do this. So you don't have this the superradiance stability for the fermionic case. So we cannot have clouds in this sense.
Okay, thank you.
Let's thank Carol again.